So on Friday, I think maybe we got a little bit lost when we were talking about photochemical smog. So I want to go through this again in maybe a bit more detail, or at least you have the opportunity to review the video later. And hopefully help clarify a few things in this process. So we've got these reactions here, reactive cycles, where you've got hydroxyl radical reacting or initiating the oxidation process for VOCs, whatever they happen to be. O2 reacting with the intermediate radicals to generate hydroperoxy radicals or just peroxy radicals, which then are oxidized by or are reacted with nitric oxide to generate NO2. And then why is it called photochemical smog as opposed to just smog? Well, it's really this process here where NO2 will absorb UVA light, which does penetrate down to ground level, and will split off an oxygen atom, which then combines with O2 to generate ozone. And this is the photochemical part. It's that photochemical splitting off of that oxygen atom, which then generates ozone in the end. And that's why it's referred to as photochemical smog. Now, in this process, VOCs and nitric oxide are the main inputs, and VOCs probably make sense. Gasoline just evaporated from a spill or emitted gasoline or diesel fuels out the tailpipe, something that's not completely reacted, or paints are another major VOC contributor. So industrial processes, it's not difficult to imagine a number of sources of VOC emissions, but nitric oxide is maybe a little bit more confusing. So on the next slide, we'll kind of go through where does that come from. Other things to keep in mind here, the main things that we're concerned with are, of course, NO2, because it's a toxic gas, but also it's the source of that kind of brown haze. Ozone, because it shouldn't be at ground level, and that's another toxic gas and leads to health problems. But these aren't the only concerns. Partially oxidized VOCs, so aldehydes that are generated in that process, carbon monoxide, these are also contributors to kind of health effects of this smog on humans. And so those are also concerns, as we'll see as we go through this. Other things to keep in mind, so we've kind of mentioned this, ozone, NO2, and partially oxidized hydrocarbons are the primary outputs of concern. But there is also another reaction to keep in mind, just ozone will react with nitric oxide as the NO is an ozone destroying agent, so we generate NO2 in that process. This is kind of why ozone levels remain low until we've consumed most of the nitric oxide that's produced or emitted into the atmosphere. But then two other things, if the NO2 concentration, if the concentration of radicals gets too high, you can get a combination between NO2 and OH to generate nitric acid, which of course that's not good for humans, and it also is a contributor to acid rain. NO can also combine with hydroxyl radical to form nitrous acid, which is semi-stable in the dark, but then is in the early morning when the sun rises, absorbs light and breaks apart to generate hydroxyl radical. This is one source of hydroxyl radical, and then also nitric oxide. So where do some of these species come from? Let's start with NO. So where does NO come from? It's primarily emitted by electric power plants and automobiles. And how does that happen? Well, it actually comes from direct reaction of atomic or molecular nitrogen and molecular oxygen. So they have two elemental forms to form two equivalents of NO. Now, this is a very endothermic process. If this happened naturally, we would all be dead because the NO would certainly react and with us as well as forming NO2, and the NO2 concentrations would be enormous and we would all die. Thankfully, this doesn't normally happen because it's so extremely endothermic. And we can kind of illustrate that here. Really, this process has to happen in two steps. First, you have to break an oxygen-oxygen bond to form individual oxygen atoms. That's uphill by quite a bit. And then that single oxygen atom has to react with N2 to form NO and a nitrogen atom. This is misdrawn here. It should be a nitrogen here instead of an oxygen. But the net thing to keep in mind here is the activation barriers are huge, which is good. These things don't happen naturally. However, if we're in the combustion engine of a car and we reach temperatures that are extremely high. So here we can see that activation barrier for that second step is very high, which is again good. But if we're at really high temperatures, up to 2000 degrees Celsius, which can be reached in internal combustion chambers, then what happens is we don't change the energy required to, we don't change the activation energy, but we do change the energy of the starting materials and the products due to all that additional heat energy or thermal energy. And that essentially just raises the energy of the starting materials, which has the net effect of lowering the net barrier for these reactions. So at very high temperatures, even though this is an endothermic reaction, we will generate enough energy to drive this reaction forward to generate nitric oxide and elemental nitrogen, which will go on and react otherwise. And at high temperatures, we have enough energy to do this, but then once we've cooled back down again, the energy barrier for the reverse reaction is too high, and so the atoms essentially are stuck or frozen in nitric oxide, in the nitric oxide form, and can't revert back to elemental oxygen and elemental nitrogen. So this is where we generate NO. Now the primary culprits, as I mentioned, internal combustion engines and electric power plants. We can see a breakdown here. This is in 2006, where most of this is coming from off-road vehicles and on-road vehicles. There is some contribution to the emissions from electric generation, from coal-fired power plants or other power plants that would get to extremely high temperatures. Now, okay, that explains NO production, but in terms of VOCs, why are they really a problem? At the end of the day, we just generate a bunch of CO2. That's not toxic. We breathe that out all the time. So where's this a problem in, how do they contribute to smog? Well, let's just take an example. Many VOCs that we're worried about have are hydrocarbons and reactive hydrocarbons. And one example is this subset here known as alkenes, so a carbon-carbon double bond. And then these R groups just stand for other carbon-hydrogen bonds, or other carbon and hydrogen groups. Well, following our flow charts, we just look at this and sort of walk through. We start with the neutral gas species. Hydroxyl radical will react with this, and we have a double bond that we can add to. So hydroxyl radical adds to this bond first, and we generate a carbon-centered radical. Now we're at a radical species. We switch over to the other flow chart. O2 will react with this, and in this case, if we just follow down through our flow chart, we'll see that O2 should add to this to generate a peroxy radical. Peroxy radical is really the top part on our radical species flow chart. So this, according to my flow chart, reacts with nitric oxide to cleave off one of those oxygen atoms and leave me with an oxygen-centered radical. Now at this point, I've got an oxygen-centered radical that's on a carbon that's also bonded to another carbon. This fits with about partway down the flow chart where we can get cleavage of the carbon-carbon bond. Essentially what's going on is this electron here is coming down to form a double bond, but it forms that double bond with one electron from this carbon-carbon single bond. So one electron goes to form the double bond. The other electron has to go somewhere, so it stays on that carbon there, and I will generate one equivalent of what's known as an aldehyde, carbon-oxygen double bond that has a hydrogen attached to the carbon, and then another radical species. If I stay on my radical flow chart and look at this radical species, I can see that if I pulled off this hydrogen here with O2, I would generate another aldehyde. So I've got two equivalents of the aldehyde. I've generated hydroperoxy radical. The hydroperoxy radical I know can react with NO to generate more NO2. And you see I've regenerated my hydroxyl radical in this process. If I take all of these steps and kind of add them together, I get to a net reaction at this point, and I'm only partially through the oxidation, but I get to a net reaction where I've got the reactive hydrocarbon, this alkene, reacting with O2 and nitric oxide to generate two equivalents of the aldehyde and two equivalents of NO2. So I'm generating NO2 in this process. So that's one of the problems, is I'm just generating a bunch of nitrogen dioxide. And then if I look at this, one issue here is that as I increase the NO2, that results in increased production of nitric acid by combination with hydroxyl radical. Also, as that NO2 that doesn't combine to form nitric acid, as that NO2 is photolyzed by absorption of UVA light, then we generate more single oxygen atoms that go on to form ozone, and that's also a problem. But we're not done with the oxidation here. We'll continue, right? We're only partially through. We've got these aldehydes, and some of these aldehydes are not good for human health, but as we'll see, some of the other intermediates are kind of a problem. So let's continue from here. Once we got to the aldehyde stage, we kind of got two pathways we can go in. The first is if I follow through my stable species flowchart, one of the things I get to is, does it absorb light and decompose? And the answer is yes for aldehydes. They do decompose. We end up breaking either the carbon R bond or the carbon hydrogen bond. In this case, if R is a carbon group, then we'll break that bond to generate a radical species, and then in this case, another radical species that's got a radical on carbon. Now I'm on the radical flow chart, so I follow through that and look at this and say, well, as I go through on the radical species, how will O2 react with this? Well, I can actually pull off a hydrogen atom from here to generate carbon monoxide, as we'll see in a moment. One thing to really highlight from the photochemical decomposition of aldehydes is that as I build up all of these aldehydes, right, I started with one molecule of VOC, generated 2 molecules of aldehydes, those will decompose and then generate a lot of free radicals in the air, which react in many different ways, some of them with our bodies, or just generate a lot more peroxy species that generate a lot more nitrogen dioxide, and you can see we just build up more nitric acid and more ozone through those processes. Going on from here, oxidation of this species here, ozone can pull off that hydrogen to form carbon monoxide. And then now I'm in a stable species. To continue that, it has to react with hydroxyl radical, which it does by addition to generate this intermediate, and then reaction with O2 to pull off this hydrogen completes the cycle. We get to CO2, but in the process, we generated 2 equivalents of hydroperoxy radical, which then also that R radical reacts with O2 to form a peroxy radical. All 3 of these react with nitric oxide to just generate this net increase in NO2. So all of these are resulting in increase in NO2, which means more nitric acid and more ozone formation, neither of which are good for you, as well as NO2 is not good for you and contributes to the brown haze. Now, the other process here is there is also a minor but important pathway where if you're at the aldehyde, rather than absorbing light and splitting apart, if an OH radical comes in and just abstracts off or pulls off a hydrogen from the aldehyde, we can generate this intermediate kind of R-C double bond O radical. What's important here is, okay, following down through my chart in terms of radical species, O2 will react with this to generate a peroxy radical. And at this point, this could undergo oxidation with NO to cleave off this oxygen atom. But if I'm under a condition where I've generated a large amount of radical species in the air, and the net result from oxidation of each of these hydroperoxy radicals is that I regenerate hydroxyl radical. If I'm at the point where I've generated a lot of hydroxyl radical, but I've also generated a lot of NO2. In this process, as I build up NO2 concentration, eventually I get to the point where rather than reacting this peroxy radical species with NO to cleave off the oxygen, I'll actually combine with NO2. And this gets me to a stable non-radical species here known as peroxyacetyl nitrate. And peroxyacetyl nitrate, even though it'll be present in very low concentrations because this is a minor pathway, is a potent eye irritant. And so this is just another contributor to all of the haze, the health effects, and the overall poor air quality that is observed during these episodes of photochemical smog. So let's go through a quick snapshot. What does a day look like in an area that's generating photochemical smog? Well, here's just an example from a day in the 1960s in Los Angeles. And if we start in the early morning, what we'll see is as the sun begins to rise, as vehicles begin to get onto the road, we start to see an increase in emissions of VOCs due to vehicle traffic, and then also as industries begin to fire up. Also an increase in NO concentration, as some of this is tied up as nitrous acid, which when the sun rises, that decomposes to hydroxyl radical and NO. And we've also got vehicle traffic, which leads to an initial increase in nitric oxide. And then we hit this point where as we begin to, as the VOC concentration rises, then that will react with hydroxyl radical. And we start to get the oxidation process of those VOCs to go to the aldehydes. So you see a little bit of a lag between the rise in VOCs and then the rise in aldehydes as those VOCs start to get oxidized. And we see an increase all the way here up to about 8 a.m. or so during rush hour traffic. And then once we've gotten over rush hour traffic, now we're no longer getting as much emissions, and the rate of oxidation now takes over. And so we start to see a decline in VOCs as there's less being emitted and more of those are being reacted with hydroxyl radical to undergo the processes that generate aldehydes. Now, during that process, we generate peroxy radicals and hydroperoxy radicals, which then convert the NO that's been generated into NO2. And so we start to see that drop and we see a rise in NO2 concentration. Now, once we start to get closer to noon, that NO that's generated, the sun has come out, we're getting photolysis or photochemical decomposition of NO2, and that starts to generate free oxygen atoms that would generate ozone. Now that ozone would react with NO that's left over to decompose back to NO2. So it's really not until that NO concentration has really dropped off via all the reaction with the peroxy radicals that we start to see rise in O3 concentration. And we see kind of this decrease in NO2 concentration as well as this is being photochemically decomposed to generate then oxygen atoms that then go on to form O3. These aldehydes rise until about noon, and then at that point, the light intensity is the greatest, so these start to undergo photochemical decomposition, and then also reactants, and so these start to decline as they're further oxidized to carbon monoxide and CO2. Ozone also peaks here as we get a lot of, as during this time with the aldehyde oxidation, we're generating a lot of hydroperoxy radicals that then are oxidized that then react with NO, so keeping the NO concentration low, and then forming NO2, but then that concentration is also kept relatively low by either conversion into nitric acid, so some of this is removed by reaction with OH for nitric acid, and then also it's being photochemically decomposed to form an oxygen atom that forms O3. And eventually, as we get late in the day, the O3 is undergoing some photochemical decomposition, and so that starts to decrease. And also as we get late in the day and the light intensity decreases, we have less photochemical decomposition of NO2, and so we generate less ozone. We start to get some photochemical decomposition. As we get rush hour traffic in the late afternoon, we generate more NO, so that concentration begins to rise. That then leads to decomposition of O3, and so we start to see ozone concentrations decrease again. So what this looks like on an average day in Los Angeles here is just this really brown haze that's the result of the high concentrations of NO2 and all of these other factors here present. I know that's a lot. Hopefully this video is not too terribly long. You'll have time to sort of go back and review some of these many interrelated reactions in this process.